All right, this is the famous open box problem. You should be familiar with this problem from last year, I hope. So we have an open box that's made from a rectangular piece of cardboard that's 15 by 10, and the squares are cut from the corners. So if you can imagine, this is just a flat piece of cardboard, and we're folding it up. First of all, we're going to cut these corners out of it, right? And then we're going to fold it up along the dotted lines, and you're going to create a box with an open top, right? So there's no top on this box. That's why it's called the open box problem, right? So part A just asks us for expressions for the length, width, and height of the box. So when the box is constructed, how long is it, how wide is it, and how tall is it? All right, so our length, our width, and our height. I'm going to start with the height, because the height, hopefully you can see, is going to be just like this. Do it in purple. This portion is going to represent the height, right? These guys here, right? Because this is the part that's going to be folded up. And this is labeled as X for us. So the height of this box is just X. Now the length and the width are made up of these portions of the rectangle. So we know that the overall length of the flat box is 15, but we're taking these corners away, right? So we're taking this guy away, and we're taking this guy away, and well, those both have a length of X. Right, so we're taking 2X away from my 15, so my length becomes 15 minus 2X, and then likewise, the width, I started with 10, but I'm taking X's away from both sides, so I have 10 minus 2X. And then use your dimensions to write an equation for the volume. So volume as a function of X. Volume we know is length times width times height, so I'm just going to take those three dimensions and plug them in to my formula. Okay, part C says find V of 3 and explain what it means. So V of 3, if I'm just going to substitute 3 in, 10 minus 2 times 3, that's 4. 15 minus 2 times 3 is 9. So it looks like that V of 3 is 108. And what does this mean? Well, this means that when that corner has a side length of X, of 3 rather, right? When the height of the box is 3, the volume of my box is 108. So when height of the box is 3, volume is 108, and that's cubic inches. All right. Part D, what's a reasonable domain for this problem? And use your calculator to graph the function. Okay, so let's talk a reasonable domain here. All right. We're talking about a box. We're limited by how long and how wide the box is, right? So if we look at the most limiting side, which is the 10, right? That's the shortest side, the most limiting side. What is the biggest value of X that we can cut out from both sides? Well, if you think about it just logically, right? If I have an X value of 5, that means I'm taking an X out from one side of 5 and the other side of 5. That's my entire 10 right there, right? So my domain cannot go bigger than 5, and it's certainly not going to go less than 0 because we're talking about a box. So my domain is going to be from 0 to 5, and even 5 is too much, so that's why we're going to use a parenthesis there, right? But I could technically go to 4.9 on both sides and have a tiny, tiny little bit of box left, right? So now why don't we consider the 15, the side length of 15? Well, if we think about it, right, if the 15 is limited, we could go all the way to 7.5 on both sides for the 15, but that's too big for the 10. So we really only consider the shortest side when we're talking about reasonable domain in these problems. And now we can go over and look and see what it looks like in a graph. All right, so you can see here that I graphed the function x times 10 minus 2x times 15 minus 2x. It is a cubic function or a polynomial function. And we don't really care about what's happening below the x-axis. we really only care about what's happening here from 0 to 5, right? But I just kind of, I extended my window a little bit just so that you can kind of see what was going on. And we're looking to maximize the volume of this box. Okay, and it looks like that maximum is occurring when x is 1.962 and when the volume is 132.03. You can use your graphing calculator to verify that point as well. Oh, okay. Looks like we answered part F first, right? It says what value of x will maximize the volume. So again, the max volume from our calculator was 132.04 cubic inches, and then the value of x at that max volume was about 1.96 inches. Okay, so we can go back to E now. E, we use your calculator to find what values of x give a volume of 126 cubic inches. So we can go back to our graph and graph the line y equals 126 and find the values of x that work there. It looks like there's two values of x in our domain that will give a volume of 126. Right? It looks like 1.5 and about 2.5. So 2.46 or 2.5 is fine. So it looks like the values of x, x equals 1.5, and when x equals about 2.5, both of those values of x will give us a volume of 126. Notice there's also one over here. We don't care about that guy because that's outside of our reasonable domain. Right, so just to finish up here, so the values of x, the values of x that give us a volume of 126 is when x equals 1.5 and when x is approximately 2.5. Both of these are inches.